I'd like to talk a little bit about two things, about slope fields and also what we call separable differential equations. So before anything else, I do want to mention what a differential equation is. Basically, a differential equation is any equation that has a derivative. And differential equations are generally of the form dy dx is equal to something. And so, like, for example, dy dx is equal to x squared minus 5x. dy dx is equal to e to the x minus 4. So those are examples of differential equations. It's stuff that you've seen before. What we haven't done before is we haven't talked about solving these types of equations, or we haven't talked about them in the way that we're going to talk about it today. You may realize that we have solved them by taking integrals, and that's the same thing that we're going to be doing today. So this right here is kind of a book definition of a separable differential equation. I wouldn't copy it down if I were you. You can find a similar thing in your book. The basic thing I want you to know about separable differential equations is that they are differential equations where you can put all of the x stuff on one side and you can put all of the y stuff on the other. I do want to point out that you'll notice that the dy is on one side and the dx is on the other. You may not have realized you could do that, but you can multiply both sides by dx. And then once you have that, you're going to take the integral. So let's go ahead and do an example. So here is a list of the steps that we're going to use. I'll work through it step by step with you, and then our first example. So we are going to be solving this differential equation, dy dx is equal to xy squared. And the other thing that they tell us is that y equals 1 when x equals 1. We're going to use this a little bit later. This is actually used in step 4 when that's our initial condition right here. You do not need that yet, but we will get to that. Okay, so let's go ahead and work with this example. So we need to separate out our variables here. What we need is we need to get the x's on one side of the equation, we need to get the y's on the other. In order to do that, we need to distribute this squared sign. So we're gonna get x squared times y squared there. The next thing that I'm going to do is I am going to take this y squared and I'm going to move that over to the side with the y, and then I'm going to take this dx and I'm going to move that over to the side with the x. So it's like I'm dividing both sides by y squared. So I get dy over y squared, and I'm multiplying both sides by dx. Keep in mind that you cannot have, if you have a dx on the bottom of a fraction or a dy on the bottom, you can't actually do anything with it. So they need to be on the top. So once we have this, we can take the integral of both sides. Some people don't like the way that I set this up, so just know that dy over y squared is the same thing as 1 over y squared times dy. That might be a little bit easier for you to look at. Now what we're going to do is we are going to integrate both sides. So the left-hand side, keep in mind this is the same as y to the negative 2 dy. We take the integral of that. We end up getting negative y to the negative 1. On the right-hand side, we get x cubed over 3. Now, it's really, really important that you, first of all, make sure that we have y and y. We have to integrate our y's together, and you have x and x here. If you don't have them separated into two different variables, you can't actually solve the problem. At least not yet. There's strategies that we have in the future when we have non-separable differential equations, but it's going to be probably at least a few semesters of calculus before you encounter anything like that. Okay, so the other thing I want you to remember on this is that these are indefinite integrals. If you have indefinite integrals, you must put a plus c. You cannot forget that constant of integration. Otherwise, you're going to get to the end of the problem and you're going to be like, why do I have this y equals 1 and x equals 1? You need to put that plus c in there. I don't actually care what side you put it on. If you put it on one side and like the person next to you puts it on the other side, one of you might have a plus c, one of you might have a minus c. That is totally fine. But you do need to have a plus c in there somewhere. If somebody had a plus c and somebody had a minus c, your final result would actually end up being the same despite that. You would just get a different value for c. One of you would get a positive, one of you would get a negative, but when you plugged it into the final equation, you would be good. Okay, so continuing on, we are going to, so we did the first thing, the separating the variables. That was what we did right here. The second thing, we integrated it, and we did it with respect to the correct variable. That's what we did on these steps right here. The next thing that we need to do, we do have to solve this for y. So that's the next thing that we'll do. When we solve for y, we have negative 1 over y is equal to x cubed over 3 plus c. This is like not an ideal problem, but we'll get it to work. That gives us negative 1 over x cubed over 3 plus c is equal to y. Like I said, not exactly what we want it to be, but in the end, we will we'll be able to solve it out. Now by the way, it's ugly, but this is a perfectly acceptable final answer if you're just asked to solve for the general equation. A general solution to a differential equation is the one that has a plus c. Now, you are given an initial condition, so that means that you're going to find the c by substituting in, this is my last step, by the way, so we did the solving for y. My very last step is going to be the solving for c, and I know that when x equals 1, y is equal to 1, so I can find the c by just substituting it into here. That should be a 1. And you can solve this in whatever way works for you. I'm going to multiply both sides by what I have right here. So I end up getting that c is equal to negative 4/3. My final answer is not c equals negative 4/3. My final answer is going to be that y equals. So I'm going to get y is equal to negative 1 over x cubed plus 3 minus 4/3. If you want to make this look a little bit nicer, this is an acceptable answer. You would get full credit for that. You can, however, if you want to make it look nicer, you can multiply the entire equation by, or the entire right side by 3 over 3, which would give you negative 3 over x cubed minus 4. So that's the answer for this one. The second thing we're going to do is draw a slope field. So to draw a slope field, you'll notice I gave you step-by-steps for this one. So a slope field is going to give us a visual depiction of the solution to the differential equation. It's basically going to be a graph of a bunch of little lines that have slopes depending on what your equation has a slope of. So I gave you the steps. The first step that we're going to do is going to be to solve your equation to for dy dx. If you look at our example below, that's done already, so it's already done. We're good there. The second part of it is I would say, I'm gonna go there and say it's the most tedious part of this, unfortunately, and that's gonna be to substitute each point that you have in your grid into the differential equation. And as you do more and more of these, you'll be able to see patterns a little better. To be honest, you don't usually need to draw the slope field. You're more likely going to have to recognize it and be able to use it. And we'll do a few examples of that. So what we're going to do is we're going to draw an XY table. But in addition to the X and the Y, we're going to draw a dy dx. By the way, you're welcome to draw this table horizontally. I usually draw it vertically, but if you are like short on room, because I think the way that my handout was listed, there's not a lot of room, draw it like this, and then you can just do it a sideways table. I'm gonna do it vertically like this because I do have enough room. So what we're gonna do is we are going to choose each point on our grid right here and substitute them into that differential equation. And then from there, we'll have a bunch of different, we'll have a bunch of different slopes. So I'm gonna start with 0, 0 is always a good place to start. So 0, 0, if I substitute in dy dx, or if I substitute that into dy dx, I get 1. Let's try another one. Let's do 0, 1, which is this one right here. If I substitute that one into dy dx, I also get 1. You'll notice, actually, this equation does not depend on y. So this one right here, 0, negative 1, again, it's still going to be 1 because there's no y in that equation. So I do want you to notice that all of the values where you have the same x value it's not going to depend on the y, so you're going to get the same slope for those. And that's going to be the case for 0, 2 and 0, negative 2. I'm not going to go ahead and do all of those. You're welcome to try those on your own, though. So the way that we're going to, and I'm kind of going a little bit out of order. We're not going to do each one, but I'm going to do the part 3 right now. What we're going to do is we are going to draw a small line segment that has a slope of whatever our dy dx is. So this dy dx, remember, is the slope of our tangent line. So we're gonna draw a little line that shows the slope of that. So each of these has a slope of 1. So you have to kind of think about what does a slope of 1 look like? Well, if you were to draw a full line, a slope of 1 would be like that. It would go up 1 and over 1. We're not drawing a full line, we're drawing a little small line segment there. So each of these, we're gonna draw a little line segment. Hopefully yours will look a little bit better than mine. These are a little bigger than that one's a little bigger than I wanted. So you have a little bit more leeway to write it because you're not writing it with your finger. The other thing is that, like I said, it doesn't depend on the y. So when you have whatever your x value is, if you have the same x value, you're going to get the same y value. So let's do a few more. Let's try x equals 1, y equals 0. If you substitute that in, you get a slope of 2. Same thing if you do x equals 1, y equals negative 1, you get a slope of 2. Actually, anywhere that x is 1, you're going to get a slope of 2. So for this one, honestly, figuring out what a slope of 2 looks like is tough. It's going to look kind of like that. If you were to draw a big slope of 2, do the best that you can. The big thing that, if you get something like this on the AP exam, and if you have this on one of my tests, the big thing that we'll be looking for is to make sure that you notice that a slope of 2 is steeper than a slope of 1. So this is going to look, all of these are going to kind of look like that. And the next one that we'll try, we'll do negative 1. So if you have x equals negative 1 and y equals 0, for example, you get a slope of 0. If you have x equals negative 1 and y equals like 2, you still get a slope of 0. Again, it doesn't depend on y. So that's going to be drawn as a horizontal line. So each of those is going to be that part of the slope field. By the way, you probably will be doing this with your pencil. Don't worry about color coding it unless you really want to. Next one, we'll do x equals negative 2. Let's do y equals 1. So if you have negative 2, 1, you get a slope of negative 1. If you have negative 2, we'll say negative 2, negative 2, you still get a slope of negative 1. Actually, anything in the negative 2 range is going to have a slope of negative 1. This should look like the one that I have in red, except exactly negative. So it's going to be kind of like this. So the last one that actually appears on this grid right here is going to be x equals 2. And I'm hoping you realize by now that no matter what your y value is, the slope or the dy dx is going to be the same for all x equals 2, and it's always going to be 3. This is going to be really hard to draw. Just try to make it look a little steeper than the blue one. Again, you're not expected to be perfect. So for example 3, you're asked to find the general solution to the differential equation from the previous example, which was dy dx is equal to x plus 1. Go ahead, pause the video, and give this a try. So for this problem, we are going to get dy is equal to x plus 1 times dx. You'll notice I took this equation and I multiplied both sides by dx. That's how I separate my variables. Then we take the integral of both sides. Be careful, the integral of dy is not 1, it's not dy, it's actually going to be y. You can write a 1 in front of there if you want to, and then think about what's the antiderivative of 1, but we need y on this side. On the right-hand side, we are going to get x squared over 2 plus x plus c. Please don't forget that c. This is my general solution. That's all I need to do to find the general solution. Now I need to find, for part B, I asked you to find the particular solution. Go ahead, if you haven't already, pause the video and try it. So they give us f of negative 2 equals 1, or in other words, we have when x equals negative 2, y equals 1. We can solve that, solve the equation with y equals 1 and x is negative 2. And when you get that, you do end up getting just that c is equal to 1. As I said before, c equals 1 is not the answer to this. The answer to this problem, the particular solution, is going to be y equals x squared over 2 plus x plus 1. Example 4 is more like what you're going to see on an AP type of exam, although they have done ones like example 3 before as free response questions. But this is probably more likely because I think mainly because it's easier to grade. So they are often going to give you a slope field. You are going to have to do some stuff with it. So the first thing they ask you to do is to sketch a solution curve through the point 0, 1. So basically what a slope field is it shows you all of the different possible values of the slopes of your equation depending on what your c value was. So the solution curve through 0, 1, we're going to draw a point at 0, 1. What you need to do to draw the curve is you need to keep in mind that these little slope lines are slopes of the tangent line. So you're going to kind of follow the way that these are curved. And so I can see that these are kind of going up like that. And then on the other side, you'll notice that they're going kind of in the opposite direction. So it's going to look kind of like this. I think this is not a perfect drawing of it, but it's a drawing that'll get you full credit. These are another one. I personally am surprised that they do these on the AP exam because I think they're hard to grade too, but the basic thing on those is just you need to realize that the little slope lines are the slopes of the tangent line. Use that to help guide your graph. So for part B, it asks you to sketch the particular solution containing f of negative 3 equals 0. Now there are actually, there are two ways to do this type of problem depending on what type of equation you have. If you have an equation that is separable, you can actually solve the differential equation out and then draw your curve. This one actually is not separable. You can try it if you want to, but you're not going to be able to do it because we have an x plus y. If it was an x times y, it would be completely okay. But when we have that plus, we're not able to solve, we're not able to get y on one side and x on the other. But what I do want you to notice is that f of negative 3 equals 0. That is equivalent to the point negative 3, 0. So you just need to figure out where negative 3, 0 is. It's actually right here. So the solution curve for that is a little weird looking. It's like this. So that's going to actually look more like that. So you can kind of see that's a little, I think, not quite. It should be going this way. So you still do need to kind of follow the guidelines there. But it's a little different looking from the previous one. That often happens on these types of problems. But just know that f of -3 = 0 is equivalent to the point -3, 0. Part C, you actually might be able to figure this out on your own. If you think you know what to do, pause the video and try it. This is stuff we've done before. So part C involves a tangent line approximation. And basically what the tangent line approximation is you need to figure out an equation. You can use y = mx plus b form. We know that the m can be found by using the dy dx up here. So m is going to be the dy dx evaluated at the point -3, 0. So that's what that actually is. And so you're going to find that the slope at that value is -3. We have the point already, it's -3, 0. So we're just going to get y equals -3x plus b. You can kind of work this out any way that you want to. And you end up getting that your b value is 9. So your tangent line is y equals -3x plus 9. We're not done with the problem, but you will get half credit if you get this far. The second thing that you need to do is you need to evaluate y of -3.1. You'll notice they use function notation for that, even though we don't usually use it with y's. That's fine. It's a similar thing to f of -3.1. So we end up getting -3 times -3.1 plus 9. That gives us 9.3 plus 9. Hopefully you end up getting 18.3.